Today we're going to focus on shear forces in thin-walled beams. So last week we covered bending moments for unsymmetrical thin-walled beams, and you should have a reasonable handle now. If I gave you a generic cross-section for a beam, you could work out the second moment of area, or the centroid, work out the second moment of area, and tell me the stress at any location in that beam due to bending moment. Now, bending moments are only one part of the load we need to consider. We're all familiar with, from statics and 2400, that beams have shear forces in them as well, and also torques, which we have to consider later on. But shear forces and torques we'll see are very similar in terms of the calculation. So with this beam that we have here, the question is, what role does shear stress play in the bending of beams? Okay, so if I gave you this cantilever beam here, and I'm not too worried about sign convention, but could you draw the shear force and bending moment diagram for this beam? Now, I'm going to mess around with the sign convention just so everything fits nicely on the board, but the shear force achieves some value underneath the load, is constant throughout the beam, and then drops back to zero at the wall where it's reacted. Okay, or it's reacted at the wall. Now you should all be fairly familiar with that. What does the bending moment do in this problem? What is it at the tip of the cantilever? Zero. Okay, so it has to be zero at the tip because there's no bending moment applied there. If we took a very small section of the beam, there's nothing to react the bending moment. So it starts at zero, and its maximum at the I'm going to use the root of the cantilever at the wall. Now, what does it do in between in this simple case? It's linear, and I don't think I can draw a straight line that long, but I'll give it a go. No, it's not very straight, but it's a straight line in between. Okay, so there's some interaction here that you intuitively know. You may not realize it, but there's a relationship between shear force and bending moment. And mathematically, we can say that the bending moment is the integral of the shear force. And obviously, with any integral, there's a constant term based on the boundary conditions. So as long as we know the boundary condition at the end where we're starting the integral, we can work out the relationship between these two things. And if I drawn my shear force with the correct sign convention, we would see that a negative shear force gives us a negative slope on our bending moment diagram. So there's obviously some relationship there, but we can think about it a bit more sensibly than that. So if the bending moment is changing as we're going along this beam, if we were to take a section, let's just imagine we took a section and sliced a piece out like this little piece here. And we'll look at that piece a little bit more closely. Now, for our little piece, remember, the shear force is constant throughout the length of the beam, but the bending moment is changing. So the stress from bending, which in this case will be tensile on the top surface and compressive on the bottom surface, but we can imagine that there's some distribution of bending stress on the right-hand edge, and there's also a distribution of bending stress on the left-hand end. Okay, and I haven't been particularly accurate with how I've drawn those, but the distribution will look something like that. Now, what's the relative magnitude of the force on this end versus the force on this end? Okay, if our bending moment is changing, now our bending moment is smaller here, and bigger here because as we're going along, there's a change in bending moment. So the net force on this end and the net force on that end, which one's bigger? The one on the left. Okay. Now, this beam is in equilibrium, so what's providing the extra force to make this piece of beam remain in equilibrium? Okay, if we're pulling harder to the left than we are to the right, there's got to be something reacting. Sorry? Yeah, so there's something happening on this face. So this face we have got some other things, but if we're looking at just say the x direction, okay. So if we're doing sum of forces in the x direction equals 0, we'll have F at the left end, F at the right end. Okay. F left minus F right plus something equals 0. Okay, sorry, this should be minus there, plus there. Now the something is a shear force. Okay. And that shear force distributed over the area is a shear stress. Now we know from little elements, if we take small pieces, so if we took a very, very, very small piece out of the middle here, something we call an infinitesimally small piece, then all the forces have to be in equilibrium on that piece, and they're equal and opposite on both sides. So if we took a very small piece, we would end up with something like this. Where there's some bending stresses, so tensile stresses due to bending, and there's some shear stresses which balance each other out. In this case, the shear stresses are going to struggle to balance each other out because we know there's no shear stress on the top. So we can't really set up an equilibrium with constant shear stresses. We would have a more complex situation. But the more complex situation is the one that we will handle today in the class. But the simple situation, we take a very small piece and assume that things don't change across the size of that small piece, is that the bending stresses are tensile on either side, and we get a set of shear stresses to balance those out. Okay. So this relationship between bending and shear force we'll actually see pop up again and again in our calculations. Now I'll do one quick introduction, and if you've seen the video over the weekend, this won't be much news to you, but we want to talk about this concept called shear flow. And shear flow is just a thin-walled way of thinking about shear stress. It just makes our calculations a little bit easier. Now, if on the top left here, we had a tube that we had applied a torque to. Okay, so we apply an external torque here. Now, we know if we take a section of that beam away, then there'll be some internal forces which will balance that external force. And if we look closely at that face, so if we zoom this face out to here, we'll get little shear stresses acting around the ring which are due to that external force. Now, the shear flow assumption basically says that for thin-walled structures, the shear stresses don't vary through the thickness. Okay, if we assume our wall is thin, then even though the shear stress may vary around the loop of the section, it doesn't vary through the section. Okay, through the wall thickness. Now, if it doesn't vary through the wall thickness, we can simplify it. Okay, and I'll do one more step here. So for thin-walled sections, we can assume that the shear stress is constant through the thickness of the section. Now, if I apply a little force to my cantilever beam again, and if I take a section somewhere here and look in on it, so I'm looking in from this end of it. Now, there'll be some shear stresses that are set up and they'll vary according to where we are in the section, but they won't vary through this way. Or if they do vary, they'll vary a very small amount. Our thin-walled assumption assumes that they don't vary that way. So what we can do, if we took our thick-walled piece and we had some shear stresses acting on it, now let's give this some dimensions. We'll assume it's the dimensions of the piece of section that we're looking at are S long. And we'll assume we've picked a small enough piece that tau is constant for at least that piece. And the thickness of our section is T. Then the force acting on that little red highlighted area is tau times S times T. Okay, remember, shear stress is just like any other stress. The force that's acting is equal to the stress times the area, and that force also has a direction. So stress has a direction. The force associated with that stress also has a direction. Okay, and that direction in the case I've drawn there is vertically up the page. Now, the thin-walled version of the same problem, we'll use shear flow. Now, we still have a thickness of our section. We still give it a parameter T, but it doesn't come into the calculations. Okay. Now, we give shear flow the symbol Q. And we define it as the shear stress times the thickness. Okay, because the shear stress is not varying through the thickness, we can just multiply those two things together and that quantity will be constant through the thickness of the section. So the force due to that shear flow is just equal to QS. So all I've done is I've taken this term and I've taken this term and I've merged them together into one object. Okay, and in exactly the same way, Q has a direction. So shear flow has a direction just like shear stress does and shear force does. Now, shear force has the units of force, obviously. Shear stress has the units of force per distance squared. And I'm writing all over the top of everything here. What units does shear flow have? Force per distance. Okay, so newtons per millimetre or pounds per inch in the units we like to use. Okay. And you can treat it just like any vector quantity. It's got a direction, it's got a magnitude, and it can vary around the section. Okay. The assumption we also make with thin-walled structures is it's always in the direction of the path as we travel around the section. So it's always in the same plane as the wall of the section on which it's acting. So Q down here would be pointing in this way. Q up here is pointing vertically, and Q over here is pointing to the right. So the direction is defined by the wall direction. So we've answered a couple of these questions. What units does shear flow have? Well, we've just said force per distance, so newtons per millimetre. What properties does it have? Well, it's got a magnitude, it's got a direction. It's just like a force in that sense. And where does it equal 0? Well, it equals 0 in places where shear stress equals 0. And that's places such as the free edges of a section. So if I go back to my cantilever beam problem again, it might be tempting for us to, if someone said, work out the shear stress distribution in this beam, if we just took our free body diagram for this section here, it might be tempting for us, assuming this was, say, H. Actually, I'll change that to Q just because we're now familiar with this shear flow. Now, it might be tempting for us to just say, if we wanted to work out what the shear flow was at any internal point, that we could just take the shear stress divided by the distance over which it acts, which is the force divided by a distance. Well, why doesn't that work? Well, it doesn't work because the distribution of shear flow changes as we go through the depth of this beam, and it changes in general around any cross section. And one of the reasons for that is if we took a really little piece out of the corner here, one of our little infinitesimal pieces. Now, because it's on this one side of that's on the surface, there's no tractions. Traction is just another word for a stress or acting on a plane. There's no tractions on the top surface because it's free. It's hanging off the edge of the beam. There's nothing acting there. So we can't have a shear flow because as soon as we take this one away and make that one 0, all the others have to equal 0 to maintain equilibrium. I'll multiply that by t just for a second. So we can have forces due to our bending stress, but we can't have shear flow at the surface. So anywhere where we get to a free edge of a beam, the shear flow must be 0. So if we get to like in our C channel, which we used as an example here, at the free edges here and here, and if I go back to my three-dimensional representation, anywhere along this edge or that edge, there's no tractions on those edges. There's no forces acting on them. So the shear flow at those points has to be 0 in the section. So it gives us a starting point for our calculations, which we'll see in a minute. Now I'm going to get very mathematical for a few slides because I need to derive a formula that we're going to use. And it does get a little bit heavy, but try and bear with me. Now this is our little cantilever beam problem that I've drawn up a few times up there. What we're going to do now is we're going to take a small piece of the beam, but we're going to not assume that everything's constant, but that the piece is small enough that we can assume that everything varies linearly across it. So we can, on one side, assume that there's a shear stress, and on the other side, assume that there's actually I'll change colour for that, sorry. One side we can assume there's a shear stress, and on the other side we'll assume there's a shear stress plus a change in that shear stress as we go along times the distance that we've gone along. So we're assuming that there's some variation from one side of our little element to the other. And our coordinates that we define are z in the length direction and s in the vertical direction. And the little piece is dz tall and ds long. Sorry, those labels are around the wrong way. And so I've used this slide for years and only just realised that. ds should be vertical and dz should be across. It should be like this. Okay. So the piece is dz long and ds tall. And we can also assume that there's changes in shear flow. So the reason I've used stress times T here is because I want this calculation to be in units of newtons per millimetre, or alternatively force per distance. Okay, so I've multiplied everything by the thickness of the beam in and out of the page. So there's a T that I haven't shown, which is in and out of the screen here. And I've multiplied everything by that T so that we can get into this force per distance set of units. It's just as valid to do it in stress space or to do it in forces, but I've used shear flows here. Now, in the same way that we assume stress can vary across our element, we'll also assume that shear flow can vary across our element. So if we've got shear flow on one side, Q, on the other side we can have Q plus dq dz dz. So we're allowing some linear variation of quantities. And if we write out our equilibrium equation in the z direction, so sum of forces in the z direction, okay, that's all this is here, is sum of forces z equals 0. Then we can say that the shear stress on the positive side times the thickness times ds, that's a force, a stress times an area, minus a stress times an area, plus a shear flow times a length, so that's a force as well. So these are all in units of force, minus a shear flow times a length equals 0. Now, luckily a whole bunch of this cancels out. This term cancels with this term cancels with this term, a bunch of other things cancel out, and we end up with a very simple equilibrium equation for this beam. And it points right back to this problem we were talking here about the relationship between bending and shear stress. The change in the shear flow and the change in the tensile stresses are related to one another. Now, I'll take a step back to last week, and here's the equation from last week that we have here. Okay, and I'm not 100% sure about my sign convention for this equation, because I know depending on the source you use, there's a different symbol, there's a different plus or minus in here. So I'm not 100% which source I've used to derive this, but I know it's internally consistent. So just bear with me. If the bending stresses, so what we're trying to do is we're trying to find Q. Okay, we're trying to find some value for Q. We know how our bending stresses vary because we derived that last week, or we didn't derive it, I showed you it last week. I showed you that the bending stresses vary around the section according to that formula. Now, if we take the derivative of that in the z direction, so the only things that vary in this equation with z are the bending moments. The cross section is not changing with z for this problem. The x and y is not a function of z. So the only thing that's changing with z are these bending moment terms here. All right. Now we've got something that we can potentially sub into our equation up the top there. But we know that the derivative of our bending moments is equal to a shear force. Okay. We take the derivative of the bending moment and we get to a shear force. Okay, and you know that from solids last year. So we can sub in shear forces instead of these dm dz terms. So now we have a relationship between bending stresses and shear force. All right, but we also, on the previous page, had a relationship between bending stresses and shear flow. So what we're trying to get to is this here, shear flow, and here changes. Okay, so it's the derivative versus constant shear forces. Okay, so we now have a formula that relates the changes in the shear flow around the section to the net forces that are on that section. So we can solve this problem. If we've got a force on one side and we want to work out what the distribution of shear flow is, we can do that now with this formula. Okay, we have to do a few more steps first because at the moment we've only got it in differential form and we have to get it into we have to integrate it. Now, we'll take the integral in ds, and by integrating in ds, what I mean is that we're going to integrate from one side of the beam to the other. So we're going to integrate from, in our coordinate system, which was s and z, we're going to integrate from the bottom of the beam up to the top of the beam. And we call that integrating in ds because we're moving along the s direction. All right. Now, our integral has to have bounds. We can't integrate, well, we can't solve for a constant term without knowing what our limits of our integral are. So our limits, we say there's some starting point, which we call naught or 0. We just give it the subscript 0. It doesn't necessarily mean that the shear force there or the shear flow there is 0. We just that's an origin term. Okay, so QS for the origin. Up to some distance along the beam S. And luckily, the only things that vary with our position are inside the integral terms here. None of this big behemoth out the front changes with position, because we've got shear forces, which are section properties, second moments of area, which are section properties. None of those things is changing internally inside the section. The only thing that's changing is the thickness, potentially, and the position. So what we're left with is our shear flow, which is what we're trying to find. A shear flow at the origin, which we'll see for simple open sections we can assume is 0, but we'll do an example of that, is equal to something times the integral of Tx ds, something times the integral of Ty ds. And it looks enormously complicated at the moment, but remember last week we said if there's any plane of symmetry for our section Ixy equals 0, so for a rectangular section or the C section that I showed for this problem, or for this problem, Ixy equals 0. Now if Ixy equals 0, big hunks of these terms disappear and cancel out. The other thing we're going to assume at the moment, it's not a general assumption, but for this problem, is that the shear forces are only acting vertically. So we're not having something in and out of the page, we're just having up and down the board. And if we make that assumption, everything collapses to this equation, and we'll see this equation over and over and over again in different guises. So it's telling us that the shear flow at any point, remember our S starts from our origin and we integrate some distance S along the section to find out the shear flow. So we're always integrating from some starting point up to somewhere where we're trying to find a quantity. So if we're trying to find Q here, we integrate from the edge or some starting point up to a point, and we can find the value of Q there. So if we want to find Q at S, we also need to know what the value was where we started. And in the problem that we've defined here, that's 0, but it's not always. So we started at a free edge, so the starting point is 0. Is equal to the external shear force in the vertical direction divided by the Ixx for the section. So again, you've seen Ixx pop up again here. So last week when I said Ixx was going to be part of every single calculation you do, it's going to be pretty close. It's appearing in shear force calculations as well. When we integrate thickness, a vertical position y, which in this case is just our position up and down the board. Y is in general the position of our integration from the neutral axis. Okay, so I didn't explain that particularly well. The y in here is the same y in our bending equation. Okay, so it's our position relative to the neutral axis. And it's just followed through in the equation. And ds. And ds is the path length that we integrate along. So we integrate along the section. Now, as I said, this QS0 term is quite important. Okay, that if we started a free edge, so say our problem was a C section like this, if we start our calculation here, and we call this our origin, then because it's a free edge, QS naught equals 0. Okay? But only because we started at a free edge. And we'll see from some, for some problems later on, there are no free edges. So if we were trying to work out what the shear flow is in a box like that, there is no free edge. So we need to have another way of calculating that term. And we'll do that after in one of the later sections of this lecture. Okay. And remembering all the time, every time you see Q, remember that it's just another way of writing shear stress. Okay, so if someone says, what's the shear stress in the section or the maximum shear stress, you first find Q and then you can calculate back from Q to stress. So it's a very common thing that's overlooked in a question. If the question asks you to find shear stress, remember that you're not there to find shear flow. You've got to do that last step at the end to divide the shear flow by the thickness to get to the shear stress. Okay, so this is a typical kind of problem, and it's the problem that is that we'll do an application for in a little while. We'll do a simpler one first, but this is the most simple problem that really illustrates how to do a calculation. The problem would be is if we had a beam that we applied an external shear force to, and the reason I've applied the shear force out here is because that's where the shear centre is, which is a concept we'll talk about later. The shear centre is out here, and if we apply an external force to the beam and we cut a section out and look at what the distribution of shear stresses is, then we can find that shear flow at any point by integrating from the bottom corner here. So if we integrate from there, we go along a certain distance s, we can find the value of the shear flow by just equating this term. Okay, so we turn problems of areas into problems of distance. When I talk about going around the section, we start somewhere and we can sort of track around our thin-walled section. So we've turned an area integral into a line integral, which solves all our solves a lot of our problems. It's still not the easiest calculation, but it's a lot easier than if we had to sum up shear stresses on every little piece of area. Okay, let's do it for the very simplest problem that we can do. The very simplest problem is a rectangular beam. Now, I've drawn it quite a stumpy cross-section for my beam there just so I could put dimensions on it. But remembering this is a thin-walled problem, so we need to have a thin section relative to our depth for our calculations to be completely valid. I've drawn it a bit bulky there just so I could label it. But now, this is just a cross-section of our cantilever. Okay, so when you see these section drawings, they're just a slice through the section at any particular point. Now we need a couple of coordinate systems here. We need a coordinate system to define our x and y. Remembering that they're relative to the centroid of the beam. And we know for this simple problem that the centroid's right in the middle, so I don't have to go and calculate my centroid location. Another coordinate system that we'll use is, because we know we have to start these calculations at free edges, I'm going to make a coordinate system starting at the bottom edge of my beam, which is S, which is where I'm going to start my integration. So I'm going to integrate along the length of the beam cross-section. The dimensions we've got are that it's D long and T thick. Okay, now we'll leave the minus SY IXX out the front because that doesn't vary. T, Y, DS. Now, for this problem, is thickness varying with S? So remember, we've got to calculate an integral here. The only things we need to keep inside the integral are things that vary in the term that we're integrating over. So does thickness vary with S? No, thickness is constant. So we can simplify things a little bit. We can make this term equal to 0 because we're starting at a free end. We can bring T outside. So we can simplify a little bit. Now, I'll just stop to make sure we're all familiar with what we're trying to do here. This S is the externally applied shear force, okay? And it's opposite in sign to the one I've done here. Upwards is positive. So if we had a shear force on the end of the beam, or if we had an internal shear force at any section, basically reading off our shear force graph here, that's this term. Okay. Thickness is the thickness of the section at any point, and IXX we know is the second moment of area. So the complicated bit in here is this Y. Now, Y is the distance of any point that we're integrating, because when we integrate we have to take little sections that are ds long and we sum all those up. Now we have to find y as a function of s. So the first thing I would say when you're trying to work out that function, I've written the function up here which you can cheat if you want to see it, but the first thing you do is you think about what the value of y is at different points. So at s equals 0, we're right at the bottom of our section. Y equals, what does y equal? Minus d over 2. At s equals d on 2, y equals 0. And at s equals d, y equals d on 2. So the simple linear function we can work out is y equals s minus d on 2. Now let's sub that into the formula and see where we get to. Okay, I've subbed that in here. S minus D on 2. Now it's just an integration problem. You all know how to do integration, although I know every time I start this lecture I have to re-exercise my mind to do integration. It's not something I do every day. But if we've got S minus D on 2 ds, we break that into two pieces. We've got an S ds and a D on 2 ds, and they're quite easy things to integrate. The first one gives us S squared on 2, and the second one gives us ds on 2. All right. Now, what this tells us, this is actually a little bit confusing. I should have written it in a different way. This ds is not this ds. I'll write this out a little bit more. Okay. We don't want to get confused with the DS's. Okay. Now that tells us, what this tells us is the distribution of shear stress through the section. So if we sub in S equals 0, we should get 0. If we sub in S equals D, we should get 0, because we know that the shear flow should be 0 at the top and bottom of our beam. What it tells us is the distribution in between, and if we plot that out, it's parabolic. Okay, so we've got a parabola in there, S squared minus SD on 2. So the shear stress, it's quite tricky to draw shear stress or shear flow on a beam section. There's two ways that we do it. One is by drawing a box that's proportional to the magnitude of the shear stress, like on the left. But that doesn't, it's not telling us anything about the direction, it's just telling us the magnitude. It's not like bending stresses. When you draw bending stresses on a section, it's telling you both the direction and the magnitude in one thing. We can't do that for shear stresses because the direction is up and down the side. We can't draw magnitude and direction in the same plot. So one way we do it is we put a direction vector to tell us which way is positive and then plot the magnitude out like this. Or the other way we do it is we just draw a series of varying length arrows that show you that there's a small shear flow here and a big shear flow in the middle and a small shear flow at the end. But for this problem, it's telling us that shear stress or shear flow, which are both linearly related to each other, is maximum at the middle of the section. Okay, and that shouldn't be too much of a surprise that as the bending stresses reach their minimum at the neutral axis is where the shear stresses reach their maximum. Okay, what we're going to do is we're going to do the first sort of complicated problem here, and I'll run this into the break. And this is the first kind of realistic problem. The rectangular section is not very realistic. This is, say, a C section. So a front spar of a wing may look like a simple C section if we had a nice straight wing. A non-tapered wing. Now, we use the corners of the section to our advantage. Integrals have the property that you can break them up. You can integrate from 0 to 1, and then you can integrate from 1 to 2 and 2 to 3, and add those together, and they'll give you the total of the integral. Okay, so we can break this integration up into pieces, integrate once from here to here, once from here to here, once from here to here, and save ourselves some effort. Okay. So let's go through that problem, and there's some slides and notes that go along with it, but I'll do most of it on the board. Okay. So just before we start, where do you predict the maximum shear flow is going to be? It should be at the neutral axis. Okay? And if we've got a symmetric problem, we'll see that we only have to calculate up until we reach the neutral axis, and then what happens on the other side will be a mirror reflection of that. So the magnitudes will get bigger as we go to here, and they'll reach a maximum, and then they'll drop off back to 0 in the same pattern, if the problem's symmetric. And I'm not going to bother for this problem to calculate SY or IXX. I'm just going to leave them as constants, but you can sub them in if you've got dimensions for your problem. What I am going to do is define some dimensions. I think I need some dimensions. I just don't want to... Okay, I'll give this some dimensions. We'll assume a constant thickness T. And depth, I just need a symbol that I'm not going to run into somewhere else. C, okay, for argument's sake. And width here, I'll call B. There's a bit of a confusing notation that goes along with this. Because we do a bunch of separate integrations, it's kind of handy to define a few different S parameters so that you know which integration you're doing. So Megson tends to start the problem by drawing on his diagrams some numbered S1, S2, and S3 to define where we do the different integrations. So let's start the problem. We'll start at 1. QS minus QS naught actually, I'm going to leave those off. I'll leave those off completely. What I'm going to write underneath my integral is, rather than put limits on it, I'm just going to say I'm integrating over S1, because that will tell me I'm integrating along this coordinate system here. Okay. If I put limits on there, it's going to get confusing with what the limits actually mean. So just a single limit tells me what the variable that I'm integrating over. Okay. We can define shear flow at a point just like we can define shear stress at a point. So the notation that Megson uses for that is Q with the subscript of the location. So Q1 would be Q at point 1, Q2 is Q at point 2, etc., etc. Now Q1 we know equals 0 because it's right on the end of the section. Okay, Q2 and Q3 we don't know. But Q4, again, equals 0. All I've done in this line is that I've changed QS0 to Q1 just to show you that the place we're starting, our origin for our integration for the first loop is Q1, which we can then cancel out and send to 0. My pens are slowly dying. Now, the only bit in here that's changing again is this y here, and it's not even changing, to be honest. So QS equals minus SY over IXX. T comes out the front. What's y as a function of S here? If we're at the top section, if we're just integrating along here, y is just C on 2. It's a constant. So it comes out the front as well. And then we've just got the integral over S1 ds. Which is just equal to S. So at any point along our first integral, the shear flow can be found by and I'm going to put S1 in here just to show that we're using our S1 coordinate. So that's not too hard. It's saying that the shear flow is linearly varying from 0 at point 1 to a maximum at point 2. So if we put in S equals 0, we'll get the value at Q1. Now, how do we get the value Q2? If we're trying to find shear flow at point 2, What do we sub in? At point 2, S1 is equal to B. Okay, because the path distance that we've gone across is B. So Q2 we've got here minus SY on IXX. Now things get trickier. So now if we want to work out the shear stress along the web, along 2, 3, what's the limit of our integration? What's the starting point, QS naught? Q2. Okay, so QS minus Q2 equals minus SY on IXX, the integral over S2 of TY ds2. Now, what we tend to do is, because we know this term is something that we've already calculated, we tend to bring it over the other side. So QS, which is our unknown, plus Q2. Okay, and we can leave that as Q2 until we need to sub in later, because we've got a nice formula for it. So we don't need to sub it in too early. So we'll just leave it as Q2. So the bit that we're really interested in here again for this integration is what's happening in here. Now, is T constant? Well, yes, for this problem. In general, T doesn't have to be constant, but the problems get tricky if it's not. The integrations just get harder. Is Y a constant now? No, so Y varies, so we need to have Y as a function of S. So I always find when I get to this point in the calculation, it's always handy to have a little diagram that I can draw beside the formula to work out what my function's going to be. Again, I'm losing pens. Okay, so this is point 2, this is point 3. My S2 starts at the top. My neutral axis is halfway in between. So my Y is measured like this. Okay, so at S2 equals 0, Y equals C on 2. At S2 S2 equals C on 2, y equals 0. And at S2 equals C, y equals minus C on 2. So as S gets bigger, y gets smaller. So we have y equals minus S and then plus C on 2. So just for the sake of clarity and not rewriting the whole shebang on the board, I'm just going to do this integral as a separate piece. And it's fine in your tutorials or your answers in exams if you just make it clear that you're doing a piece of the calculation independently, that's all right. Okay. The S part goes to S squared on 2. The C on 2 goes to S C on 2. Now check to see whether this is going to be right. If you put in S2 equals 0, your answer should come back out to be Q2 again. Okay, so this whole term has to go to 0 when S2 equals 0, because otherwise you've got something here that you shouldn't have. All right, let's chuck that up. Actually, I'll keep that up. I don't want to rub that off. That's pretty important. Okay, so let's revisit the line up the top there. The second bottom line. Okay, so this is telling us the variation of shear flow as we go along. So where do you expect that to be maximum? At S2 equals C on 2. And you'll see that that term is biggest when you put C on 2 in there. If you put something bigger than C on 2, this term dominates and starts getting smaller. If you put something less than C on 2, you've got to, you start at 0, you build up to a maximum, and then you drop off again. So if we wanted to find the maximum, we could actually put another point in on our section, and we'll just call this, for argument's sake, 5. We don't have to necessarily redo our calculation, but we could, if we know that the maximum is going to be there, we can say Q5 equals, and we can sub in C on 2 to work that out. And that's important if we want to know the maximum value on the section. So that we'll do that. Let's sub in S2 equals C on 2 and see what we get. Minus SY on IXX T minus C squared on 8 plus C squared on 4 plus, where did it go? I rubbed it off. Minus SYT on IXX. I think it was just BC, wasn't it? There's no other.
No, BC on 2.
BC on 2. Yes, okay. All right. Okay, so for us to find the maximum, we can rearrange this a little bit more. Minus SY on IXX. T can come out the front, and inside the brackets we would end up with C squared on 8 plus BC on 2. So that would be the maximum shear stress on the section. And if you weren't sure, if it wasn't clear where the maximum was going to be, the maximum is going to be here because we know it's a symmetric problem. If you weren't clear where it was going to be maximum, you could differentiate this and work out where it equaled 0, where the derivative equals 0, and then solve for that point. Any questions? Now, before we go too far, I want to talk about sign here. There's this minus sign that's hanging around out the front. Now, what does sign mean with shear flow? Well, we know that shear flow, the direction of the shear flow is defined by the direction of the wall. But what does a positive or negative sign mean? A positive sign means that the shear flow is acting in the direction that we're integrating, and a negative sign means it's acting opposite to the direction we're integrating. So we've chosen a path. When we start this problem, we could have started here and meandered this way around the section, but we started this way and are going around. What the minus sign tells us, if everything in here is positive, this is positive, the minus sign's telling us that the shear flow is acting opposite to the way that we were travelling. Okay, because we were integrating that way, the shear flow is acting in the opposite direction. Okay, and I'm going to shortcut the rest of the calculation, but I'd ask you to have a go at it just to convince yourself that it's true. I can write down that Q3 equals Q2 and that Q4 equals 0. But it will come out of the maths here. If you kept this integration going for the next, or if you subbed in S2 equals C, you would get that. And if you subbed in, if you did the next bit of the integration, you'd go back to 0. Okay, and I just want you to convince yourselves that that's the case. But the magnitude of Q because it's a symmetric problem, the magnitude of Q goes up to a maximum and then drops away back to 0 in exactly the same pattern. Because everywhere here where there's a positive y, there's the same negative y. So the integration, what would have been a positive y here becomes a negative y. The integrations head back towards 0. Okay. What's the end goal of all of this? Well, I've drawn a lot of sections on the board that look like C's and straight sections, and you might be thinking, well, how do we get from this to a real aircraft problem? So I want to introduce the kind of aircraft problem that we might have, and I'll show you that we're still a few steps away from it, but we can get there, and we'll get pretty close to it next week and get closer again the week after. The kind of problem we might have is a wing section, for instance. We know that wings look like cantilever beams hanging out off the side of the fuselage. There's some distributed forces applied to that wing. There's some lifts and some weights. We can put hard point loads in for engines and work out what a shear force and bending moment diagram for the wing would be. So at any section, we can go along and say, well, what's the shear force? Say we wanted to work out at this section what the shear forces were. Well, we can work out what the shear force is and the bending moment is. But that doesn't really tell us about what's happening to the material. For the material, we need stresses. We need bending stresses and we need shear stresses. So if we had a wing section that looked something like this, where we had our wing box, and our wing box is defined by the front spar, the rear spar, and the skins on either side. We have a wing box and a leading edge section and a missing trailing edge because there's often a control surface here that is not structural. If we wanted to work out what the shear stresses were in that, we could apply a shear force. We could work out what our shear flow distribution was around this section, and obviously this is a much more complicated shape than this one, but the maths is still the same. There's a couple of little tricks that we'll need to get to that point. The first is we need to work out what happens with closed sections. So we've always dealt with open sections to this point where there's a nice easy starting point at one end or the other of the section. With closed sections, there's no easy starting points. The other thing we have to work out what to do is to work out what do we do with the stiffeners. Do we have to work out the distribution on each stiffener and the spar caps and all that complication? Well, next week we'll work out an idealization process which makes that calculation easier. We can just assume that the stiffeners just are a fixed area and we don't have to integrate over them. So that simplifies that step. So now we've got most of the way there. And the last step, which will be the lecture after the break, will be how do we handle dual sections where we've got a closed box and an open box, two closed boxes side by side, or a closed one and an open one. How do we handle the fact that we've got two sections here and the integration doesn't work very well for two sections, which we'll see. Okay, I'll just close this door. So what we're going to do is we're going to take the next step. We're going to take the next step towards this problem up the top, and the next step towards that problem is to be able to solve a shear flow problem like that. Okay, assuming we've got a shear force applied to it, what's the shear flow distribution inside of that box? Now, we can see the formula here. And for the previous questions, we had a nice starting point. We had somewhere where we knew QS naught equals 0. For closed sections, we don't know that in general. When you've got some experience, you can sort of work out places where it might be 0. But in general, for a problem that you're faced with, we don't know where to start. So what we have to do is actually invoke another equilibrium equation. All the equilibrium equations we used for open section were sum of forces. So all the derivation that we were using was sum of forces. Now, because we've got a closed section and we can't, sum of forces doesn't give us everything we need, we have to invoke a sum of moments to solve the problem. We don't, there's an extra equation needed. So it's like we've got a set of simultaneous equations. Not only have we got sum of forces, we need sum of moments in order to solve. Now, moments, because we've only dealt with forces so far, moments we need a moment arm. And the symbol we generally use for our moment arm is P. Okay. And we also need to take moments at a point. About a point, sorry. Okay. So the P's are all defined relative to that point. So the process is as such, and I think I may have flipped some screens around here. We'll see in a second. But what we do, here's our section. And we artificially pick a starting point, which in a lot of the parlance of Megson and in some of the tutorials I use, we call cutting the section. So it's sort of artificially making it an open section. And we assume that the two little endpoints, which are very close together, have this unknown, as of this stage, value for the shear flow, QS naught. So we just leave it, we just call it QS naught and leave it in all the equations. And it's going to be constant anyway, because all the calculations, remember when you do your integration, you're always adding the bit from the previous calculation. So this QS naught is going to be everywhere. And in every place we solve for Q, there's going to be this constant plus QS naught hanging off the end of the equation. It's just constant everywhere in the section. So another name for it is the constant shear flow, because it doesn't change as we move around the section. The other part of the shear flow that we're solving for just so that we know that it's different from the total shear flow, before we were writing QS, which was telling us that we were solving for the total shear flow. Now we know that we've cheated. We've sort of broken a part away. The bit that's left over we call QB. So and this in Megson terms is basic shear flow. I don't know why he chose basic, but QB stands for basic. So the thing that we're trying to solve for is here. We've made a cut, and there's going to be in all our calculations this constant QS naught hanging around. So what we do is we treat it like an open section, solve it like an open section for QB, and then we work out, we use moments. So we use forces to calculate this term, and we use moments to calculate the last term. Let me just check what's on the next slide for a second. I can't see it very well here. Okay. So this is the solution process. Calculate IXX and find centroid. Well, that's the starting point for any calculation. Cut the section. So here I've cut it on the right, but you can cut it anywhere. It doesn't matter. The numbers as you go through the question will be different, but the total answer will always be the same. So don't be afraid to cut it anywhere. As we'll see in the adaptive tutorials, there are some convenient places to cut it which make your life a bit easier, but it doesn't really matter. Solve it as if it's an open section. So start at the cut, go around the loop in the same way as you did with an open section. And we call that QB. And then we use moment equilibrium, and I'll explain the moment equilibrium in a second. So this is our slide to demonstrate moment equilibrium. So let's assume we take moments for the external forces about this little red dot here, about this point. Okay, and we're just going to work out moments in an anti-clockwise positive fashion for the sake of this calculation. Now, if the moment of the external forces and the moment of the internal forces is the same, about this same point, so again we're doing a clockwise positive calculation about that point, then this equation holds. And the terms in this equation are the shear force, the distance of the shear force from our, like the moment arm for the shear force is this bit here, okay? So the external forces are on the left, the internal ones are on the right, and the internal moments are P, which is the moment arm at any point. So if we're working out, I might zoom in here maybe. If we're working out shear forces, the moment of the shear flow here, the P is just the perpendicular distance to that shear flow. It's like it's the moment arm that creates the moment. Okay. Now, we can break that integral up, and the other thing you may not be familiar with, this little integral symbol here means integrating around the loop. So because we've got a closed section, we integrate the whole way around. Okay, so just starting at one point and coming back to the same point. Now we can break our loop integral into two pieces. We can have one bit that's our basic shear flows, so our open section, our pretend open section shear flows, and another bit which is the constant bit that flows, is constant all the way around. So what we've done is, if we had QS equals QB plus QS naught, which I've got up there, I've just done an integral for this bit and an integral for this bit separately. So the top line is this, and the next line is just split out into two pieces. Okay. Now, because QS naught is constant, it doesn't vary with S. It's the same anywhere. We can take it outside the integral. And if we take Q outside the integral, we end up with this funny integral PdS. And if I draw that out, and you'll have to suspend your disbelief for a little while, because I'm not going to go through the derivation for this. But I'll give you a rough explanation for why it is. If we were to pick a point here and measure the perpendicular distance to any point, P, okay, and we summed up as we went all the way around, so we did a loop integral of PdS, summed up all the way around, any shape, so I've drawn a wiggly shape so that you don't think it's just for squares or something. It's equal to 2 times the area that's inside here. And I put little funny brackets around it because I want to say the enclosed area. So it's not the area of the wall thickness, it's the area inside the shape. And the reason that is if we think about this, okay, P times ds is a little triangle, okay? And, sorry, it's a little rectangle. So ds and p. Now, we can sum up lots of little triangles to make up this area. And those little triangles are all going to be exactly half that area. So the enclosed area is going to equal the sum of half of PDS. So if you rearrange that, you end up with this up here. Okay. So now we have something we can actually solve for, because the bit that we were missing, we've got a tool to solve for QB. We know how to calculate A for most shapes, but we couldn't get to working out what our real shear flows were without knowing what this term was. And we didn't have a way of calculating that, but now we do. We just rearrange that equation at the bottom there. QS naught equals the integral of PQ ds over 2a. Okay. We rearrange that formula. And then we sum this bit that we've calculated to this bit that we've just calculated to give us the one that we're after. Okay, and I'm actually not going to do an example of this right now because I'll do an example later on when we've got a bit more detail. But a typical question would look like this. Okay, we've got a square hollow section that has got a 1 kilonewton shear force on the end of it. And you could think this was a really poorly designed plane wing, I suppose. Someone could be trying to force this through the air hanging out the side of a plane. But there's a shear force applied to the end of it, and we've got to work out the shear flows inside. The process is to cut, pick a starting point, work out the shear flows around, and then solve for this QS naught, and then work out what our QS is. Okay. And if we get time at the end, I'll do an example with this and another question wrapped together. Okay, I'm going to take a seemingly a bit of a detour here, but we'll see that they converge together fairly quickly. I'm going to talk about torsion and twist of sections. And we'll see that torsion and twist are very, very closely related to shear. At least for thin-walled problems. So, has anyone seen a torque diagram before? You can make a torque diagram just like you can make a shear force or a bending moment diagram. Okay. If we had a shaft, and again you've got to kind of draw these in 3 dimensions to make them meaningful. Let's just assume we've got a different section there. And we can put a torque on here. We can put a torque on there. And we can have a reacting torque Okay, because we tend to call this engineering system a shaft, whereas what we've talked about so far is a beam. But in practice, a wing of an aircraft is both a shaft and a beam. It takes bending, shear forces, and twist. Because as you apply aerodynamic loads, those aerodynamic loads don't all act in one plane. There's a twist to them as well. So we'll see that the twist is sort of tightly knit into the calculation. Now, what would a torque diagram for this look like? Okay, again, I'm not worried about sign convention here. There is a proper sign convention for this, which you can check in Megson, but I'm just going to draw it here. We might go one way from that torque. This torque might be, if this torque is bigger than that one, it'll go negative, and then it'll, say, come back to 0. Okay. So torque, just like shear forces, we can draw a diagram for. And we can have distributed torques as well. There's nothing saying that we have to have torques only at one place. We could have a torque that was distributed over a section. Okay, and that might create a linear section in our actually, based on my directions there, I'd have to go the other way. Okay, that might create a linear section in our diagram. Okay, so there's no, the rules for torque diagrams are very much the same as rules for shear force and bending moment diagrams. Now, the torque aerodynamically comes from the fact that there's a twist generated by the airflow. So if we look, and I'm not very good at drawing airfoils because I'm not an aerodynamicist and I don't like aerodynamics very much. And so there's some pressure distribution on a wing when you fly it through the air. Okay, and those pressures act normal to the surface. Okay. Now, if you sum that up, there's a net force to that. Okay. And that force might have a point of reaction somewhere. But we generally, from a structural perspective, transfer that force to the aerodynamic centre as a force and a moment. Okay, actually I think I've drawn my... Oh, no, I think I've drawn the moment the right way. Anyway, regardless of whether I've drawn this the right way or not, the reason we pick the aerodynamic centre to apply this to is because although the force changes with angle of attack, the moment relative to the aerodynamic centre changes a very small amount. So it's an easier place to do our calculations because we don't have to include a DCM, d alpha term in our calculations. Okay? And when you start doing some dynamics of aircraft, that term will just complicate things. So we pick a point just so that we can have d lift, d alpha, or dCl d alpha, that's fine, but we don't have change of moments. Okay, so if we think about this, if we think now, rather than our fancy aerodynamic shape, that we're trying to fly a square hollow box through the air, we need to work out what the effect of the torques on that box are going to be. Okay, because again, this thing, who knows what the pressure distribution is going to look like on our box? It's going to be horrible. But they'll probably, if it's not symmetric, there'll probably be some torque. Now, it turns out that closed sections are very good at resisting torque, but open sections are very poor at resisting torque. And there's an example in the tutorial questions which I would urge you to have a go at. If you just take like a paper towel roll holder, like a cardboard tube of any thin-walled section, and you twist it, it's very stiff. It doesn't twist very much for the amount of torque that you give it. If you take a pair of scissors and cut a little slice down one side, so you haven't removed any material, all you've done is just chop the section in one place, you can twist it with no force whatsoever. And it can be a factor of maybe 1,000 times the torsional stiffness difference, just because one section's open and one section's closed. The reason that for open sections are so bad at resisting torque is because you can't resist it with shear flows. Our basic assumption that the shear stress is constant throughout the section is not valid. Okay. There's never a way of setting up for a pure torque a way of reacting it with shear stresses. Okay? The way it's reacted in a closed box or a closed tube, if we apply an external torque, the internal shear flows react it, and that's not possible with an open section. What actually happens is that you end up with stress couples. So you end up with a shear stress being positive on one side of the section and negative on the other side of the section all the way around, and it's the differential between those stress couples which reacts the torque. And it means that our assumption for shear flow is not, you cannot calculate shear flow for torque on an open section. Q is meaningless. It's not that it's zero or that it's some value that we can't calculate. Our very assumption that tau equals is a constant doesn't hold for that problem. So this shear flow idea is nonsense. Okay. And so what we can do, however, is calculate how much twist we might get for a given applied torque. Because these things do have some resistance to torque, it's just not through shear flows. Now, the approximation that we'll use is the one that's given here. So our typical measurement of torsional stiffness is the amount of change of twist of the section for the change in the length. So imagine we had a tube that we'd marked these kind of grid lines on that were all straight along the tube, and then we applied a torque to it. All those grid lines are going to now be at an angle, although I haven't drawn it particularly well. they're all going to twist around relative to their initial position. And I should have drawn them a bit more exaggerated than I have. Okay, but the angle of that twist, assuming that's a small amount of torque and we're not completely twisting our beam to pieces, the angle of those grid lines after the twist versus the initial position, which we can call theta, which is also the amount that if we looked at the end of a section and we marked a point and we twisted the section, it would move around theta into its new position. Okay. So the amount of twist per length that we go along is a measure of how torsionally stiff our section is. So obviously if we've got a beam that's 10 metres long and a beam that's a metre long, we'll get a different amount of twist for the same torque because there's more material, like it's a bigger spring. But a way of comparing one beam to another is by the amount that they twist per section of length. And I mean, we can assume that it's going to be proportional to the torque. So a bigger torque applied, a bigger amount of twist, that makes sense. And it's inversely proportional to the shear modulus of the material. So the shear modulus is related to the Young's modulus. So the stiffer the material, the lower the amount of twist. The thing in here that we need to work out is what's called or I don't know the name of this J actually. In other terms, it's the polar moment of inertia. I'm not exactly sure what the name of it is in this case. But it's the resistance of the section to being twisted. Okay, so it's much like IXX. It has a similar set of units. Okay, we've got it's in distance to the fourth. And for a narrow strip of material, it's equal to the length of the material times the thickness cubed over 3. If we build up a section out of narrow strips, so one narrow strip, another narrow strip, another narrow strip, the J is just a sum of ST cubed on 3. Okay, very quick example. Let's use the same dimensions we had before. Okay, and we'll work out the rate of twist. So another name for this is the rate of twist. Okay. If we have a torque T and we have a shear modulus G, what's the rate of twist for this section? Okay, and you could sub in numbers here, but I'm not going to. Just as an aside, does anyone remember the relationship between G and E? Hmm? 2, 1, 1 plus nu, I think it is. I never remember the exact particulars of where the 2 and the 1 go, but I believe it's that. So E for aluminium is about 70,000. G is about 27,000 megapascals. Okay. Don't quote me on that, but I'm pretty confident about that. Okay. So let's work out our J. J is the sum of everywhere in the section of ST cubed on 3, which is, for the top part, BT cubed on 3. For the web, CT cubed on 3. And for the bottom flange, BT cubed on 3. Which we could call this, I suppose, S for the section. So it's the sum of the area, the sum of the length of material that we've got around our section. Okay, because we go B, C, B. So d theta, again my pen's going. D theta dz equals T on G T cubed 2B plus C. Okay, so obviously without numbers in there we can't get an idea of what the magnitude of that is, but it's significantly lower than for other sections, because we'll see here, sorry, significantly higher, because we're getting more twist per length than other sections, because we've got a T cubed here. And from all our talk to date, T is small relative to the other dimensions in the section. So T cubed is going to be a small term, which is going to dominate the bottom half of this. So we're going to get very big twists per torque that's applied. Okay. Now, for a closed section where we can get a torque reaction around the section, the maths is really, really easy. Okay, so we know from right back at the equilibrium that we did right at the beginning that dq ds and dq dz are related to each other, although they're both, the shear force is 0, so they're 0. Okay, so therefore if Q is not changing, if there's no change in Q with S or no change in Q with Z, then it's a constant. It's a nice easy constant. Okay, and if it's a constant, we can do our moment equilibrium again, and our external moments are the torque, our internal moments are this integral QPds. Now, because Q is constant, it comes out the front, and we just end up with 2AQ. So on our box section that we were talking about before, if we apply a torque to that, then Q is just equal to torque over 2A. And that's constant anywhere in the section. Now you might be starting to get a feeling that this Q, which is constant, and our QS naught are kind of related to one another. And we'll see soon that they are related to one another. Because remember, we found QS naught by doing a moment equilibrium, and we found Q by doing a moment equilibrium. Turns out they're fairly interchangeable. Depending on where we apply our forces, we can kind of switch between these at will. Now the rate of twist, and it turns out this rate of twist calculation is actually quite important later on when we start doing built up sections with multiple boxes in them, that the rate of twist, which we can find by this seemingly complicated equation up here, and again I'm going to give that to you without derivation, but the derivation is in Megson. Now let's just think about what this means here. And this is the general rate of twist formula. This isn't just for torque, but this is the general one. It's saying that for closed sections where we can calculate a Q around the section, the amount of twist is, on the top here, it's proportional to the shear flow and the length of the section divided by the shear modulus and the thickness. Okay, so it's saying that for sections with lots of wall in them, we'll get more twist. But what it's inversely proportional to is this enclosed area. So it means that bigger sections that have a larger area inside them, so if this is our section 1 and section 2, a bigger section will have less twist in general, because this term will go up faster than this term. For our torque case, the twist of a section with a torque applied is just torque on 4 times the area inside squared times the integral of ds over gt. Now, gt in most cases is constant. This is a material parameter. It doesn't have to be constant. If we had a box with multiple materials, we could have a varying g. Again, t doesn't have to be constant. We could have varying thicknesses around the box if we wanted to. But an integral ds is really just telling us to sum up the circumference of our section. So integral ds is really just saying how long's this, how long's this, how long's this, how long's this, how long's this. We'll just add them up. And it's the same here. Okay, we're just adding up the lengths. But if we compare this formula to this one, which is up here on the board, this has got a t cubed on the bottom of it. Okay? So the thickness of the wall is the thing that's really driving the twist. This one's got an a squared on the bottom of it, so the enclosed area. So even though our wall thickness is tiny, our enclosed area can be quite big. Okay, we're talking about the whole inside of the space of a wing or whole inside of a fuselage or something. So we've got a huge amount of area enclosed by the section. So our d theta dz for closed sections is very small. Okay, it's tiny. D theta dz for closed. D theta dz for open sections is big. So I just want to take a quick moment to talk about these shear flows that we've looked at so far. And just give you a bit of perspective on what they mean in 3 dimensions. Because I find, and I've found from experience, everyone gets very good at calculating these things in a section plane, but they don't really appreciate what it means in 3 dimensions. Now, say we had our C section that we apply a shear force at the end of. Now, it turns out that regardless of where we take the section, the shear forces are going to be constant, or the shear flows are going to be constant at any section that we take. So let's just pick one of them. And we know now, based on our calculation earlier, that the shear flows do that. Okay, but what does that mean in 3 dimensions? What are we actually drawing there? Well, if I put the 3rd dimension in, we can imagine a little element of material here. And that element of material, if I flatten it out, has got a shear flow on one side. But to balance that, it needs a shear flow on the other side, and it needs a pair of shear flows. Okay, and I haven't drawn this as a square, but if it was a square, they would all be equal. If it's not a square, these ones won't be the same magnitude. But what it's telling us is that in 3D, if we've got a problem like this, if you've got shear flows acting on a section cut, so this is just looking closely at a section cut like this, they actually represent little boxes of shear flow. So the whole thing is actually being twisted by these shear flows. So at any microscopic point, there's a whole little system of shear stresses acting. There's not like one thing acting on the edge of a section. This is happening everywhere. And if you imagine you started with a grid pattern on your test or on your section that looked like this, then as you applied the shear flows, that grid would start to distort. Okay. So the shear flow, which is the equivalent of shear stress, is creating a shear strain, and it's stretching and twisting our sections. Okay, and that combines our rate of twist. This is why our rate of twist, okay, has a shear flow in it, because it's the shear stress that's creating this twisting action. There's one more big concept I want to introduce, and it's the shear centre. Okay, we have not been very explicit about where our shear forces have been applied so far. Now, if we had a rectangular box, and remember this is a 3-dimensional thing, I'm only showing a cross-section of it, and on the end of the box we applied a shear force here, at this line of action. Remember, a force has a line of action. We could equally say that we've applied a shear force here and a moment, or a torque, because those two force systems are the same. There's no... Externally, we could do either of those things. So there's nothing really to differentiate shear forces from moments because we can move the force anywhere that we want. We'll just get a different moment. So what we actually need, additionally to the shear force, we need some information about where it's acting. And we generally use this xi symbol. Okay, but additional to the shear force and the torque that might be applied to this section, we need to know where that shear force is being applied. And the most common place that we'll assume it's applied, unless we say otherwise, is this place called the shear centre. Okay, and the shear centre is the point on any cross-section at which an applied shear force produces no twist. And this is very carefully worded. Twist here. That's not torque, okay? So there's a point which you would have now been introduced to through the lab if you went, called the shear centre, where as you're applying the little masses, the beam was twisting when you're on one side of the shear centre and it was twisting the other way when you're on the other side of the shear centre. But at that shear centre point, the beam didn't twist at all. Okay, so there's this point that's defined as the shear centre. It's quite important for open sections. Okay, for open sections like what we've got here, the shear centre, it's very important to apply shear forces near the shear centre, otherwise you'll get a large amount of twist. So just have a guess and chat to the person beside you if you're not sure, and if you've done the lab you should be able to answer most of these, where the shear centre is for these 5 sections that I've drawn. Okay? So we did this for centroids, now we'll do it for shear centres as well, and the shear centre and the centroid don't have to be at the same position. They can actually be at very different positions. Okay, so if there's an axis or a centre of symmetry, the shear centre has to be there. Because if we just spun our view around 180 degrees or flipped it in a mirror, we'd still have to see the same thing. So for this Z section, it's right in the middle. For the I section, it's right in the middle. So that's told us those ones. Our C only has one plane of symmetry, so it lies somewhere on the plane of symmetry of our C, but we don't know where yet. For our T section, it lies somewhere on the plane of symmetry of our T. And the next rule we can apply is if all the arms, so all the flanges of a cross section are straight and incident on a single point, then that's the shear centre. So for our T, the shear centre is there. For our L, the shear centre is there. The C is the only one that we haven't worked out yet, and if you've done the lab, you know the answer. So there's a plane of symmetry here. We know that the shear centre must lie somewhere on it. So I'll actually be able to get a good gauge of who's done the lab now. Who says the shear centre would be over here somewhere? Hands up. No? Here somewhere? No? Out here? Okay, so I know. No one's willing to put their hand up because it's about there. Okay? So the shear centre's outside the section. Okay? And it's not on the section in the C case. Okay? And so if we apply a shear force at that point, this section won't twist. If we apply a shear force to the left of that, it will twist clockwise. And if we apply it to the right of that, it'll twist anti-clockwise. Now the big question is, how do we calculate where it is? With an open section, the shear centre is the point where the moment from the external loads is equal to the moment from the internal shear flow. Okay, because remember we said that shear flow for open sections is only meaningful when we apply a shear force. If we apply a torque, the meaning of shear flow kind of drops away. So any torque that we can apply, if we move our shear force from the shear centre, we'll be applying a twist, which will induce a torque on the section. So we need, if we're applying it at the shear centre, then there's sum of the internal moments here equal to sum of the external moments. And again, we're seeing this moment term here, integral PQ ds. And if we divide by the magnitude of the shear force, we find the distance. And a word of a warning, anytime you see a moment equation, this should immediately jump out as a moment equation to you. Anytime you see a moment equation, be very careful about signs, because with forces, it's very easy to get your sign convention right. You just say up the page or across the page. But with these kind of equations, the sign depends heavily on how the initial drawing was set up. So for this particular drawing, I've got a positive moment here. If I had the SY on the other side, I'd end up with a minus sign out the front. And Megson, I can't remember which way around he is, but he has either a minus or a plus here, and there's either the opposite on the other term. But you've just got to be, every time you see a moment equation of any sort, not just shear flow kind of moment equations, take a step back and just make sure you've got your signs correct. Don't just rely on the formula to give you the right answer. Okay, for a closed section, moment equilibrium is always guaranteed. We don't need moment equilibrium in a closed section. So how do we find the shear centre? Well, we have to use the definition of the shear centre, which is the point where you apply a force where rate of twist equals 0. Okay, so moments we know are okay, that we can't get anything from moments. So let's go to the rate of twist. This is the rate of twist here. Now, if we're assuming that's 0, we sub in 0 on the left-hand side. We've got our internal shear flows on the other side. We separate our shear flows into the basic term and the QS naught as we did before. We can then bring the QS naught out the front. And if we've got QS naught out the front, we can solve for that, which gives us the value for QS naught down here. So we get it as the integral of the basic shear flows around the loop times the path length over the integral of the path length. Now, once we know QS naught, then we can sub it in here and we can find the shear centre location. And because this is quite an involved calculation, I'm going to do an example of it, and it'll kind of wrap up a lot of the closed section and open section things that we've been talking about. We might not get all the way through it, but we'll give it a go. Okay, I'm going to use a section which we kind of know the answer for before we even start, which is a rectangle with a constant wall thickness. So we know that because there's two planes of symmetry here, the shear centre is going to be right in the middle. So I'm telling you where the answer is going to be before we start, but we'll calculate it and see whether we get the same thing. So, the solution process. What we're going to do is we're going to give this some dimensions first. Okay, T, C, and B. So the first part of any question which has an IXX in it is to find centroid and IXX. Okay, in this case we'll just leave it as IXX because we could calculate it here, but it's not particularly useful for us. Now, for finding the shear centre, all of our calculations for the shear centre have this QB involved. So we have to work out the basic shear flows. And to calculate the basic shear flows, we have to cut the section somewhere. Now, I'm going to cut the section here. Now, for the moment, we're going to have an unknown shear force acting at an unknown, or sorry, a constant shear force acting at an unknown distance from our front wall here. Okay, pounds. Killing me. So, first step, cut section and find our basic shear flow. So we can do that. And I promise you that next week, I know that this is going to be very integral heavy. I promise you next week I will show you a trick to get rid of all the integrals. So I'll only subject you to the pain for 1 week. Okay, but you still need to know how to do it because it gives you a more correct answer. Okay. One, two, three, four. We're going to number our section up like this. So now the way my subscripts are going to work is Q basic 1 instead of Q1. I'm just going to put a B in there so that I remind myself that it's a shear flow at it's a basic shear flow. It's a pretend open section shear flow equals 0 because I made a cut in my section here. Now y in this case is just equal to s. We're starting at the same point. Okay, so we just get s squared on 2. Now for bookkeeping purposes, so that I remember what I'm going to have a lot of these formulas. So for bookkeeping purposes, I will call this QB12, which is telling me that it's the shear flow somewhere between 1 and 2. QB2 equals, if I sub in C on 2, I get minus SY on IXX T C squared on 8. QB23 equals minus SY on IXX, the integral over S2 plus QB2 I'll keep that one for the moment. Rub this one. Now y in this case is just C on 2, so we'll get C on 2 S2 in there. Plus QB2 okay. Now I'm not going to bother subbing in the value there. We'll just, I know you can sub in from up there down to there. QB3, if we sub in B into there, QB3 is minus SY on IXX, T, BC on 2. Plus, what have we got up there? Okay, you can see these calculations are getting pretty massive pretty quickly. Now, my function of y for 3 to 4 S3 equals 0, at y equals c on 2, S3 equals c on 2 at y equals 0. So y equals minus S3 plus c on 2. So we get minus S3 squared on 2 plus S3C on 2 plus QB3. C squared on 8, C squared on 4, plus C squared on 8, plus C squared on 8 gives me C squared on 4, C squared on 4 plus BC on 2. Okay, so I've done this a few times so I can kind of track through it very quickly. I'm not expecting you guys to go through too many of these. There's one tutorial problem where you have to go through it. And there's one adaptive tutorial problem as well. Now, I can also say that from 4 to, for the other half of the section which I haven't shown, from 4 around to 1 is going to be the same thing, just flipped over. Okay, so if I have to calculate any loop integrals or anything, I can just double them because I'm going to get the same thing on the bottom side. All right, so that's step 2 of a lot of steps in this question. The next step is find QS naught. Okay, because remember we cut the section. We need to find the unknown value of Q at that cut. And to do that, we use this approach here. What am I doing? Okay, so we're assuming the shear force is applied at the shear centre, so it simplifies our calculation pretty dramatically there. QB ds on integral around the loop of ds. Okay. So the top half of this equation is going to get nasty. The bottom half is really easy. What's integral around the loop of ds? Just adding up all the wall lengths. Integral around the loop ds is equal to 2b plus 2c. Okay, I'm just adding up all the wall lengths of the section. Hopefully these pens are a bit better now. Now to do the top bit is much trickier. To do this, we're in a world of pain. Because the integral, we can break this up because we're going to go around the loop. QB12 ds plus the integral from 2 to 3 of QB23 ds plus the integral from 3 to 4 of QB34 ds. And then because we've got a mirrored section, we can just double that. Now, what this is saying, you've got to reintegrate these formulas with respect to S. Okay, so you're taking these and then you're doing another integral with respect to S. All right, so this is going to get pretty involved, so I obviously don't have time to do that here. And then once you've got this, this will be a number, this will be a number, and this gives us the value of QS0. And the last step is to find our Xi value using this moment equation, okay? But in there, again, we've got to do another integral to get there. So one problem of finding the shear centre in this case is integration upon integration upon integration upon integration upon integration. So I promise you I'll only make you go through that for 1 week, and then next week we'll do an idealization process to make some approximations that will make this a little bit simpler.